Hi, and welcome back. Today's lesson 3.2, logarithmic functions and their graphs. If you guys took a look at your Canvas page, you'll see that we are talking about the definition of an inverse of a function. And we talked about in chapters 1 or 2, we talked about a function having one-to-one, and in the case where it had one-to-one, we knew that it also could have an inverse. So if we look at these exponential functions that we have been dealing with, this is perhaps base a, y equals a to the x. We can see taking this horizontal line and moving it up and down, we would actually never hit the graph in more than one spot. So this horizontal line test just proved with this function that it is one-to-one and therefore has an inverse. Well, we talk about the log functions in relationship to the exponential functions because they are indeed inverses of one another. And we're going to be looking at that fact and how it applies to us. If you'll look at page 192, definition of logarithmic functions, we are going to consider x always being greater than 0 for now, a being greater than 0, and a not equaling 1, just as in the exponential functions that gave us a constant value. Then we have the definition of the logarithmic function y equals the log base a of x. This is if and only if, we're going to abbreviate, x is equal to a to the y power. Well, let's look at that. The function given here, f of x equals log base ax, called the logarithmic function. From the definition above, we can see that every log equation can be written in an equivalent exponential form, and every exponential equation can be written in log form. The equations are y equals log base a of x and x equals a to the y. They are equivalent. When evaluating logs, remember that a log is an exponent. This means that log base a x, just written like this, is the exponent to which a must be raised. A must be raised to what power in order to equal x? So if we had this written out, let's look at an example. For instance, log base 2 8. What we're asking here, 2 raised to what power is 8? Our solution would be 3. 2 to the third power is 8. So that's how we look at a log function. A to what power gives us that x value. So let's look at example 1, and using the definition of log functions to evaluate each log at the indicated value of x. If our function is log base 2 x, and we want to evaluate x at 32. So what we're saying is log base 2 32. What we're saying is 2 to what power is 32? Well, we just saw that 2 to the third power was 8. If we multiply by 2 more, we're at the fourth power, we're at 16. One more power, the fifth power, we are at 32. So we write log base 2 32 equals 5. We say f of 32 of log base 2 32 equals 5. So go ahead and look those over in example 1. We're going to assess part B, log base 3x. We want x to equal 1. Let's just look at that one quickly. Log base 3x. It says allow x to equal 1. Log base 3, 1. What we're saying is 3 to what power is 1? Will result in 1? Well, anything to the 0 power is 1. So we know that log base 3, 1 is equal to 0. Go ahead and look through C and D in example 1, and then try checkpoint down at the bottom of page 192. Let's try exercise 23 in the problem set and meet right back here. So we found problem 23. It's asking log base 2x when x is 16. So we're asking again to what power is going to give us x, the value 16, which they've given. And so counting by powers of 2, 2, 4, 8, 16, we see that 4 powers of 2 gives us the equivalent x value that they've asked us to get. I'd like to look at problem 24 as well. It gets a little trickier. Problem 24 looks like this. It's saying log base 16x, log base 16x, and we want to assess that when x is 1/4. So what we're saying is 16 to what power will yield 1/4? Well, 1 over anything, we know that our power needs to be a negative. And when we look at the relationship between 16 and 4, I realize that the square root of 16 is 4. And the way to write the square root as a power is as 1/2. If we just wrote to the positive 1/2, our value would be 4. Because of that negative, we know that square root jumps into the denominator, and we can assess the functions with that information as well. So right above example 2 on page 193, we can see that we're going to start talking about the common log, natural log related to e, the common log related to base 10. So the log function with base 10 is called the common logarithmic function. On most calculators, you see your button with an LOG. This will indicate base 10. When we see the natural log, LN, this indicates a base of e, which we talked about as 1 plus 1 over x to the x, an approximation of that value, the natural log 2.718, ... Okay, so we're going to be talking about base 10. If you look at example 2, it's just getting you used to the idea of evaluating different x values. So log base 10 x. When we don't see the 10 there and we see LOG, we understand and know that that is base 10 if it's not written. If they want us to convert that to a different base, then they'll write that, and we'll go over that later. So if I want to evaluate this at these different x values, log of 10, now in comparison to natural log, this is just saying 10 to what power is 10? And we know that to be 1. If we look at the next one there, B, it says log base 10 of 2.5. This is a calculator problem. We're going to enter log and then simply 2.5 and enter. And your calculator will give you that value. It is 0.3979, says the book. Now let's think about that. With that answer, we're saying 10 to what power is 2.5? Well, 10 to the 1 is 10. 10 to the 1/2 is the square root of 10. So 10 to the roughly 4/10 or 2/5 would make sense that we get a value far less than the base that we started with. So as with any function or concept in math, we're going to have properties. We have properties of exponents. We have properties of operations. We have all sorts of properties that we deal with. I want you to look on 193 and look at these properties of logs. The first one says log A 1 equals 0 because A to the 0, doesn't matter what that base is, anything to the 0 power equals 1. First property. Second property, log base A. This is saying A to what power equals A? Well, we know that to be 1. True, always, and forever. The third one, log base A to the x, is saying A to the what power is A to the x. And we know that to be x. We look over here. A to what power is A to the x? Of course, it is x. And that's that second part we will go over later. And then part 4, it says if log base A x is equal to log base A y, then x has to equal y. And that should make perfect sense. Please look at example 3. Look through all those and their solutions, A, B, C, and D, and then try exercise 31, and we'll meet right back here. All this is saying to us right here is 7 to some power is x, which is equal to 7 to some power, which is 9. And we can gather from this that same power, because these are equal, these powers are equal, and we can conclude that x equals 9. 7, log base 7, 9 is log base 7, 9. So at the top of page 194, looking at graphs of log functions, in order to sketch the graph y equals log base A x, we keep in mind that it is the inverse function of the exponential function. Log base ax is the inverse of y equals a to the x. So with that in mind, we can simply take a graph of the exponential function and remember the part where a function and its inverse are always reflected across the line y equals x. So if we're able to graph the exponential function, we can simply reflect it across that line y equals x to see our log function. Looking at example 4, they are graphing the function y equals 2 to the x, the exponential function, and comparing that to y equals log base